Welcome back to the deep dive. Today we are uh, plunging headfirst into something I think a lot of you are dealing with, the nexus of enterprise Java and the generative AI revolution.
Yeah, and for anyone building in the Spring ecosystem, this is, well, it's a must listen.
Our mission is pretty direct. We're unpacking the practical architecture, the actual programming techniques that let you, as a Java developer, build sophisticated, production-ready AI applications. We're finally moving past that Python-centric narrative.
And that hunger for Java integration, it's a direct result of how AI itself has evolved. I mean, we've moved so far beyond traditional machine learning.
Totally.
We're now in this world of large language models, LLMs, and they're defined by just sheer scale,
Yeah.
billions of parameters. And they can handle multimodal data, text, images.
We're talking about the big ones, right? The GPT series, BERT.
Exactly, the state of the art. GPT, Google's BERT, which is known for its deep bidirectional understanding, Meta's Llama, and now these enterprise models like IBM Granite and Mistral are getting serious traction.
That is the powerhouse we need to connect to. So the core challenge for a developer, especially JVM developers, how do you tap into that power without getting bogged down or making huge architectural compromises?
Right.
Our goal today is to show you how to bridge that gap between your Java stack and these massive LLMs, starting with, I guess, the most fundamental bottleneck they all share.
Exactly. And that starting point, the very first hurdle any developer hits with a raw LLM is something called the context window.
The context window. It sounds technical, but it has immediate, really practical consequences. So if it's basically the LLM's short-term memory, what happens when you try to run a long, detailed business process through it?
It's a hard constraint. It's a critical limitation. The context window defines the maximum amount of information, the prompt, the instructions, the final response, all of it that the model can see in one turn.
And even the big new models have this.
Oh, yeah. Even something as powerful as GPT-4o has a strict limit. It's around 128,000 tokens. That sounds like a lot.
Does sound big.
But once you start feeding it complex business rules or multiple documents or a long chat history, you hit that ceiling fast.
And that hard limit is precisely why a raw LLM, straight out of the box, just can't handle proprietary enterprise data. You can't fit a company's entire policy manual into a single prompt.
And that's why Spring AI has emerged as such an elegant solution for the Java world. It draws inspiration from Python projects like LangChain, sure, but its whole purpose is to provide these foundational abstractions. It just streamlines the complexity.
And it lets you talk to all those different models we mentioned.
Yes. It unifies the interaction with OpenAI, Llama, Granite, all of it through one standard component. The chat client.
The chat client. So that becomes your one single interface no matter which model you plug in on the back end.
Yeah.
That's a huge deal for maintainability.
It is. And we saw a great Hello World example of this. A developer can just set up a standard Spring Boot app, use the chat client to handle a simple G@T request, and immediately get a text generation response. Ask for a Shakespeare quote, get one back.
It just works.
It just works. The fundamental ease of integration is right there from the start.
Okay, so Spring AI handles the integration part. But to manage that enterprise scale, the massive data stores, we still have to get around the context window itself. Which brings us to, I think, the most important pattern in enterprise AI right now. Retrieval-Augmented Generation, RAG.
RAG it's non-negotiable for enterprise applications. It's the foundational pattern for connecting an LLM to your private internal data.
So you're giving the LLM a library to read from before it answers.
Exactly. An instant, massive, domain-specific reference library.
So how does that work? It's got to be more than just pointing it at a folder of PDFs.
Oh, way more. This is what we call the naive RAG process, and it has two main phases. First is the indexing phase, or the ETL phase. This happens offline. You take your raw data documents, manuals, whatever, you clean it, you segment it into smaller chunks, and then you convert those chunks into vector embeddings.
Okay, stop right there. Vector embeddings. For those of us not living in data science, what are we actually doing? We're turning paragraphs into lists of numbers. Why?
We're basically turning language into geometry. Vector embeddings are these high-dimensional numerical representations of text. And the key is that the distance between two vectors represents how similar the original text is.
So closer numbers means closer meaning.
Exactly. And computers can do that kind of math similarity searches way, way faster and more accurately than they can do old-school keyword searching across billions of documents.
So math is just better than keyword searching. And where do these numerical representations live?
In a specialized vector database. For a Java developer, this often means using something you probably already have. PostgreSQL with the PG vector extension.
So PG Vector just extends PostgreSQL. You don't need a whole new database system.
You don't. It extends your existing robust stack to handle this vector indexing and searching. It's great for getting RAG operational. Which brings us to the second phase, retrieval and generation at runtime.
This is when the user asks a question.
All right, your question also gets vectorized. And that vector is used to do a similarity search in the database to find the most relevant chunks of your data.
The top K chunks, as they call it.
Correct. And this is the most crucial part. Those retrieved chunks are then dynamically inserted right alongside your original query to create a single, highly specific prompt for the LLM.
Ah, so the LLM isn't guessing anymore. It's effectively reading the answer from the source material you just handed it.
Wow.
That has to cut down on hallucinations.
Dramatically. And we saw great examples of this. First with unstructured data, like ingesting a massive PDF, so a CVS Health annual report, and then being able to ask specific questions about it.
And it works for structured data too, which I thought was fascinating.
Yeah, that was a compelling example. They ingested a bikes.json file, just a file full of product details, and the system could then answer a detailed query like, what are the specs for the Hyperdrive Turbo X1? And the answer comes back completely factual, sourced right from that JSON.
But RAG isn't a silver bullet. I mean, solving the context window problem sounds like it creates a whole new set of governance problems.
It absolutely does. The moment you connect an LLM to your internal data, you introduce huge challenges around data quality, privacy, and compliance. If you're pulling health records, you have to have strict anonymization. You need robust audit trails.
Right, you need to prove how the AI got its answer.
Exactly. The complexity shifts from just getting the answer to proving the answer is safe and compliant.
And that focus on safety leads us perfectly into the next layer. We figured out what data the AI uses with RG. Now we need to focus on how the AI thinks. This is all about advanced conversational techniques, prompt engineering.
It really is an engineering discipline now. It's not just about writing a simple text string anymore. It's become as structured as, say, managing views in a Spring MVC app. The sources highlighted two powerhouse techniques. The first one is chain of thought prompting, or SOKU.
Chain of thought. Letting the AI show its work. Why is that so important for the enterprise?
Because the enterprise needs coherence. It needs to reduce errors. COS forces the model to break down a complex query like a request for nuanced financial advice into a series of smaller, logical steps. By forcing that human-like reasoning process, the model's final response is just. It's far more coherent and relevant.
So code increases the internal stability. But the second technique, ReACT, takes that even further by making the whole reasoning process visible.
Yes, that's ReACT, Reason and Act. ReACT is this incredible fusion of RAG's retrieval with the LLM's generative power. It forces the AI to output not just an answer, but its explicit thinking steps in a structured format. Thought, action, observation, and conclusion.
I can see the benefit there immediately. You can actually follow along.
The benefit for you, the developer, the user, is total transparency. You see the AI's internal reasoning. Why did it search the database? What did it find? It makes the system so much more interpretable, trustworthy, and effective.
Interpretability and action. That's the perfect segue. We've managed the data input, we've made the thinking sound. Now the AI needs to actually do something in the real world, and that means function calling.
Function calling is maybe the most exciting piece because it turns the LLM from a fancy search engine into a real coordination layer. It's the mechanism that lets the AI interact with your external APIs and microservices.
So walk us through the architecture in Spring AI for this. It builds on existing Spring patterns, right?
Absolutely. You start by registering your business logic. Your Java functions, which are just standard Spring Beans, get registered with Spring AI. This tells the LLM, in plain language, what tools it has. I can look up weather, I can check inventory.
So the LLM gets a user prompt like, what's the weather in Dallas?
Exactly. The LLM analyzes that prompt, looked at its list of registered functions, and decides, okay, I need the weather service. Now, it doesn't execute the function itself. This is key. It generates a standard JSON object that describes the function call and its arguments like city, Dallas, and it sends that JSON back to Spring AI.
So Spring AI catches that JSON payload, runs the real Java code, and then sends the result back to the AI.
Precisely. Spring AI translates that JSON into a call to your weather service bean. The function runs, hits a real API, gets the result, 97 degrees and sunny, and returns that factual data to the LLM. Then the LLM generates the final natural language response. The current temperature in Dallas is 97 degrees.
That system is what enables real automation. And this is where it got really interesting. With that GSA facilities management use case, that was an incredibly complex real-world orchestration.
That example blew me away because a single user prompt, give me 2 available buildings in Anchorage with contact info and the current weather, that one question triggered 3 totally distinct functions.
3 separate backend systems, wasn't that?
Yeah. First, a leasing service called a local Spring Data REST API to query a PostgreSQL database. Second, a contact info service did actual web scraping with JSoup to parse a GSA website for contact info.
Wow, so a real external resource hit.
A real scrape. And third, a weather service called a totally separate external third-party API for the weather.
The level of coordination there is astonishing, but it also raises questions. What if the web scrape fails? Does the whole thing just collapse?
And that's why the architecture is so vital. The LLM's job isn't just to call functions, but to synthesize the results. It takes the data from all 3 of those systems, the database, the scraper, the API, and it weaves it all together into a single, unified tabular response. It's a natural language coordination layer for your microservices.
Okay, so now that we have all these pieces working together, RAG for data, RESUT for thinking, function calling for action, we have to talk about moving this from a cool prototype into the real world. We have to talk governance and LLMOps.
Absolutely. And when we talk LLMOps, we need to differentiate it from traditional MLOps. MLOps is very focused on model versioning and data pipelines. LLMOps expands on that. It's focused on prompt management, prompt versioning, and managing the pretty significant computational needs for inference.
For a Java developer, what does that focus on computation really mean? Is that an infrastructure problem?
It's a bridge between infra and dev. For you, it means optimizing memory usage in the JVM. It means containerization, making sure your Spring AI app runs efficiently in Docker or Kubernetes. And most importantly, it means treating your prompt templates like source code. They need to be version controlled and tested.
And what about the big governance themes? How do we make sure these apps are safe and reliable?
We identified 3 core themes. First is explainability. You have to be able to justify the AI's output. Can't deploy what you can't explain. Second is fairness and no unjust bias. You have to mitigate bias from the training data. And finally, accountability. That means clear ownership and robust logging tied back to tools like GitLab or Jira.
That's the big picture. Let's zoom in on the tool inside Spring AI itself for managing prompt quality. That's the relevancy evaluator.
Right, that's the practical tool you, the developer, will use day one. The relevancy evaluator is basically an interface designed for testing the quality of your prompt against the ARA context you've provided.
So you're testing the AI's knowledge boundaries using standard Java tools like JNet.
Precisely. We saw a great JNet example. A test passed with a score of 1.0 when the user asked about the cheapest bike, because that data was in the vector store. But the test failed immediately, scored a 0.0 when the user asked something irrelevant like, what's the history of the S&P 500 when you've only loaded bike data?
It prevents the AI from just making stuff up.
It prevents speculation. It keeps the AI grounded in your verified enterprise knowledge base. It's the crucial step for trusting these apps.
This has been a complete journey. We went from the basic constraint of the context window to solving it with ARG, enhancing interactions with Cotin and RESUT, automating actions with function calling, and finally, governing it all with the relevance evaluator to get to production.
And as a final takeaway for you, for the listener, consider a huge future trend that's going to impact all of this, the rise of small language models, or SLMs. We've focused on these giant LLMs, but SLMs are designed with millions of parameters, not billions. They're built for efficiency, low latency, and deployment on resource-limited environments, even edge devices.
What's the implication there? If smaller models get really good at specific domains, it could change the whole architecture.
Well, given the enterprise's constant need for speed and efficiency, the provocative question for you is this. How might the emergence of these highly efficient, domain-specific SLMs transform the design of your future Spring AI applications? Could it push intelligence closer to the user and reduce your dependence on these massive, costly, centralized models?
A fantastic thought to mull over as you start building. Thank you for joining us in this deep dive. We'll see you next time.